when you consider first semester, the basis for all of kinematics begins with Newton's second law. This is where we begin. Now, that's not where we end, but it is where we begin. Let me make sure that the screen is good. Yeah, it'll do. Starting here builds first a foundation for energy. So that begins with the definition of work, which, if we consider the two ways we looked at work, there's work done by any force. And then, of course, we had the concept of work done by a net force, which was different in that work done by any force doesn't really tell you how it changes the system, but work done by a net force led to a change in kinetic energy. And that created our definition for kinetic energy as well, with M serving the part of inertia here. It's important to make that distinction. That's what this M is about as well. The whole concept here is based on the idea that objects have inertia, and in order to change their motion, you must apply a force. That is Newton's second law. The effectiveness of that force does depend on the inertia of the object or the system. But everything else after that relies on the inertia of the system to tell you how the object is responding. Thus, kinetic energy, 1/2 mv squared. Although the velocity seems to be more prominent there, it is the inertial mass that's used in kinetic energy. We also know that if we look at it from a different standpoint, how long a force acts on an object, that this causes a change in momentum, with a big distinction here being that momentum is a vector quantity. But still, it comes back to the idea that we are changing something about the motion of the object. Well, this is all translational. And it's not a surprise, nor are you surprised, that there is a corollary for each one of these when it comes to rotational motion. Now, about a week ago, we were able to prove that net torque is a direct extension of net force. And although I went through that rather quickly, we didn't use it. We just talked about how the moment of inertia is related directly to the individual shape of the object. But it still represents inertia, that the effectiveness of a torque will depend on the inertia of the object. The more effective the torque is, the more it's able to accelerate the object. But often, that effectiveness is based on how easy or difficult it is to get that object to move. It should not be a surprise then that we're going to have a new way of expressing work, something that has to do with the work done by a torque. Either individual torques acting on an object, or, as we might come to show, the effectiveness of a net torque over some angular displacement, which is likely to lead to a change in rotational kinetic energy. If we're keeping the same parallels going, it shouldn't be hard to predict that rotational kinetic energy is a direct extension of the individual motion of pieces of the object. So just like we talked about for force, we'll probably have something similar for energy. That rotational kinetic energy is a direct extension of the inertia and the velocity. And I don't think it's too far an extension to consider that there's likely to be an impulse for torque. Now, There is an important distinction here, though. Energy is energy. Always will be. So there's lots of forms of energy. And when we look here, we're seeing torque times delta theta, but theta is going to be in radians and doesn't lend any units, so we get our unit of meter Newton or Newton meter, which is a joule. However, time does lend units, suggesting that impulse is going to produce a change in rotational momentum. We use capital L for rotational momentum or angular momentum. But that angular momentum is not going to be the same unit as linear momentum. In fact, angular momentum is different enough that it will require its own unit, its own discussion. So we'll discuss angular motion as a separate and completely distinct topic. It's got some challenges ahead of us to deal with angular momentum. So these are, although parallels, they're not all necessarily representing the same thing. So we want to focus today on dynamics and really emphasize Newton's second law for dynamics. Our first example is to go back to what we talked about first semester. And I'm going to draw this problem out. I don't think you need to draw it into your notes. This is just to act as a reminder of something we've already learned about and to give us a little bit of a starting point. You should recognize this as an Atwood machine. So you guys remember these problems, right? In these problems, we assumed a couple of things, and I want to remind you a couple of things that we assumed. First, we tended to assume that the pulley was massless, and therefore we were able to make the distinction that the tension in the cables were the same everywhere within the cable. Those are some of the things we did before. In these problems, the acceleration of the system was related to the inertia of the system, but also the acceleration of the system was based on the unbalanced force that acted on the system. So usually if you are sharp and remember last year, let me write this different. We would be able to solve to find that the acceleration of the system fits a known pattern. Net force equals MA is what we tended to see, with the net force showing up here and the total inertia of the system being in the denominator. If you were to work this problem out, that was usually the solution for these. Now, there were things that could change that. If there was friction acting here, we know that would play a role in changing what we'd get for the acceleration. But these problems usually began with creating a free body diagram for the masses, recognizing what masses were acting on what, and how these things were related to the overall motion of the system. Now, getting the answer usually wasn't terribly difficult, and most of you acclimated to this pretty well. It required, though, generally, that you came up with a consistent direction that you called positive, and we tended to base that on the direction that the pulley was going to turn. That motion for the object that was falling had to be in the same direction, or consistently considered the same direction as objects that were moving on the table. This was a modified Atwood machine, and no matter what version of this we discussed, generally solving these problems wasn't too challenging after you kind of figured your way through it. In the beginning, it was very challenging for a lot of you. Well, our pulleys no longer are massless. Our pulleys have mass. That's going to introduce a couple of problems that you probably have not foreseen. The first and the most, I don't know how to say this, probably the most surprising to you is that we can no longer assume the tension in the cable is uniform. I want you to really consider what you write down here in your notes. So although I said you didn't have to draw the picture, what you do need to come away with here is some pieces of information that are different than what you've been trained on so far. I want you to think for a moment that there's clearly going to be tension created in this cable. We know there has to be, because the block doesn't fall straight downwards to the ground. The block accelerates downward based on the net force acting on it. Now that suggests there's a tension acting downwards on the pulley. And up till this point, we would assume that these two tensions are the same, and that's a good assumption. But we've also gone so far as to suggest that this tension acts also on the mass. But that can't be true any longer. And the reason is the pulley. If the pulley has mass, then by Newton's second law for torque, the only way the pulley can accelerate, because the pulley now has a moment of inertia, the only way it can accelerate is if there's an unbalanced torque. Meaning there are two torques acting at the edge of the pulley. They can't be equal. So this has to become T1, and now we assume that over here is T2. And that they are not equal. Moreover, it's probably very likely that T1 has to be greater than T2. If we believe the pulley is going to rotate in a clockwise direction, then the clockwise torque has to be larger than the counterclockwise torque. That's going to be the first implication of having to have mass attached now to our pulley systems. And this shouldn't be a surprise. We should expect our systems to move slower when the pulleys have inertia. Because now the net force hasn't changed. The net force is still the weight that was hung. But now our entire system has increased the inertia of the system because the pulleys have inertia. Bless you. And therefore I expect that the force that's going to act on that mass on the table is going to have to be less than it was before. You can kind of say that the pulley used up some of the force in order to get itself moving. Now we're going to see this in practice today with what I hope is the simplest example of this that I can offer. This is our original starting problem. We're going to use a massive pulley, and I don't mean like huge massive, I just mean that it has mass. And this massive pulley is held in place by a bracket so that it will stay in place here, but that we are going to hang a box off the side of the pulley. Like so. Now, I want it to be known that the box doesn't just fall to the ground, that it will take a torque to cause the pulley to turn, and the pulley has inertia. By the way, this shouldn't be a huge surprise, but we saw this the other day. The thing that I had sitting up on the table where I was allowing the weight to fall in order for the apparatus to spin, that's what this is. The apparatus is the pulley. It has inertia. And the box that's falling is the falling mass that we used over there. It didn't fall at G. It fell slowly, depending on how much inertia the pulley had. Let's go ahead and establish a few things first. Let's assume that the pulley is held in place here at its center of mass. Let's also assume that the pulley has a radius r and a mass capital M. And let's assume the pulley is a disk, which means it will have moment of inertia 1/2 mr squared. Let's also now state that the hanging box has mass lowercase m, and that this system is joined together by a thin massless cord. Now, at this point in your study, you should be able to tell me what torque is acting on the pulley, and you should be able to construct a Newton's second law force equation for the mass that is hung. I'll give you 2 minutes before I call out a couple of you to help me write these down. Although some of you have parts of the right answer, let's start with the box. Creating a net force equation here should not have been a struggle. So for those of you who struggled, you need to pick your game up a little bit. So 2 arrows perhaps, one smaller than the other. A moment to identify what direction we're going to call positive. A net force equals lowercase ma. And I'm thinking mg and tension, so mg minus t equals ma. That should not have been a challenge. A little disappointed by the number of you who were challenged there. I'm thinking if the tension's acting here, it's also acting here, especially since I just showed that in the last one. Here's where I saw the real problems. I just asked you to calculate what the torque is. Not the result of the torque, but what the torque is. How many forces act on the pulley? There's at least 3. At least 3. If we assume frictionless, then only 3. But the pulley has mass, so you're going to have mg acting on the pulley. The bracket is likely holding the pulley in place, because I said it was, which means there's an upward force from the bracket. What do you want to call it? Normal force? Doesn't really matter. You need a name for it. And all the names are just placeholders anyways. And then there's clearly tension acting downwards. Now, I didn't say to do this, but it should not be too much to expect that you know the net force on the pulley is 0. It stays in place. But also asking you to recognize that there will be an upward force that acts on the pulley that is greater than the weight of the pulley, I think is important. Being asked about this force is not unusual. And that normal force is actually somewhat complicated, because that normal force will depend on tension, and tension will depend on how this mass is accelerating. So the upwards normal force will not be the weight of both the pulley and the box. It'll be less than that, because one of the boxes is falling. So it doesn't pull up with the complete weight of the system. This is asked about all over the place on the exam. So being able to recognize about this normal force or supporting force and how to get to it is going to be important. But you weren't asked to do that. You were asked just to calculate the torque acting on that wheel or on that pulley. And if the pivot is located here, then neither of these two forces cause a torque about the pivot, but the tension does. So you should have immediately recognized that there are 3 things to consider when calculating the torque on the pulley. I didn't ask about the result. I just asked about the torque. So what's the size of the torque arm? We use capital R, the radius of the pulley. What is causing this torque? Tension. And what's the sine? What's the angle? I'm sorry, I'll ask you this way. What's the angle between the tension and the radius? 90. Yeah. If it's a pulley, then our angle will always be 90 degrees because our tension will always be a tangent. So all you had to show was that the torque was RT. Now, a lot of you went further. Great. But I'm not sure you knew what you were doing when you went further. Because I guarantee you, this is not mg like a lot of you wrote down. Now, before we go any further, is there any doubt that under this situation, the pulley is going to turn this way? And is there any doubt that the mass is going to fall this way? Now, this part is hard. It seems easy now, but trust me, this part is hard because I just have to change a little bit, and this is dramatically different. You need to spend a moment and decide whether this can adequately be used in your problem. You need to see if the rotation of your object is related to the linear motion of any other part of your system. Spend a moment in problems to evaluate that before you go on. This one is bonehead easy. I mean, I think we could all agree that if the pulley goes around once, the weight falls one circumference. That clearly links these things together. But it doesn't have to be like that. So you need to spend a moment and evaluate that and make sure you know how the motion of one object is related to the other. You should also spend adequate and sufficient time to make a clear and conscious decision about what you will call positive and be consistent about it. I'm going to call the clockwise motion of the pulley positive in the same way that I'm going to say downwards is positive. That allows me to use this to link these things together. Because there's a single torque acting in the system. Therefore, the net torque being equal to I alpha suggests RT is equal to 1/2 mr squared times alpha. This is the application of Newton's second law applied to the pulley. So the pulley will have an acceleration related to its inertia and the unbalanced net torque acting on its edge. At the same time, the box is going to experience an acceleration due to the unbalanced forces acting upon it. As you might have come to expect, the tension connects these two things together. But because one of them is rotational, it's going to have angular acceleration and not linear acceleration. If you want these problems to go better for you, I would encourage you to consider always using the linear acceleration to link the problem together. Meaning, once you reach this point, you actually have 2 equations and 3 unknowns: tension, angular acceleration, and linear acceleration. Deciding if you can use this becomes incredibly important. Because if you can, then you can reduce it to 2 unknowns. Also, the reason why I want you to put this in terms of the linear acceleration is you will often find that r cancels out completely when you do. Do the math here, you'll notice that we had r squared here, cancels out with the one r in the denominator there and cancels out with the other r that was causing the torque here. Doesn't always happen this way, but it does a lot of the time. Meaning that the tension equals 1/2 capital M times A. Now we're back to the kind of problem we did first semester. All right, we can find acceleration or we can find tension. Now, I don't know what your notes look like. If your notes look like what's on the board, they mean nothing to you. You're going to look at them tomorrow when I ask you to do this for a pop quiz, and you're not going to know where to begin because all you have is a group of, well, alphabet soup all over the place. If I was just to put this screen on the board without any explanation, it'd be hard-pressed to know where I even began. So do you have notes that tell you what happened here in the order in which it might occur? I'm going to go through it real briefly. And I'm doing this mostly for folks who are seeing this for the first time, although this was discussed in AP Physics 1. But I would encourage you to maybe list a set of steps. Number 1, draw a free body diagram for the object that can move, that has translational motion. Apply Newton's second law to it. Next, evaluate the forces acting on the rotating object. Consider if those forces cause the object to accelerate or not. Identify any torques that act on the object from that list of forces. Apply Newton's laws to torque. Look for a common direction of motion. And assess positive and negative direction. Look for a common direction of motion and assess positive and negative. Consider carefully how the linear motion is related to the angular motion. Consider carefully how the linear motion is related to the angular motion. Convert everything to linear motion. Now, tomorrow, I want you to come to school with this problem attempted. It's a toilet paper problem. If you don't know what I mean I want you to hold the end of a toilet paper and let it roll out under your hand. Like so. Remember that last year? That's 2/3 G. That's the acceleration of the toilet paper if we assume the toilet paper is a disk. I'd like you to have tried calculating that tonight. The answer should be 2/3 G if you assume that it's a disk.